Welcome back, everybody. So we're here to start chapter 5. So we're going to cover really kind of two main topics. 5.1 is really reviewing logarithm functions, and then 5.2 is getting into differentiation and integration of those functions. So for 5.1, I kind of have just a one-page summary, which again you can look over. The starting point is really important though. So we're going to define the log function a little bit differently in order to make our derivative process a little bit more streamlined. So the natural log function, ln of x, which again is just log base e, is defined by the following equation. So we're actually going to define it as an integral function, which might seem kind of weird. Like, why are we making this an integral function? But we'll see that that's actually going to make it really, really easy to apply derivative rules as well as integral rules to this function. So this definition is very well known. You'll find it in most textbooks. So we can just kind of look at Desmos here to see how it derives that function for us. So if we look at y is equal to the natural log of x, we get this nice red curve that looks like our normal natural log function. So increasing 1 to 1, has a vertical asymptote at x equals 0 and is approaching negative infinity from the right. And then on the other direction, it's slowly increasing as we increase values of x. So if we graph the function defined by the integral from 1 to x of 1 over t dt, what we end up with is the exact same function, right? And what this means is that the derivative of the natural log function, which is f prime of x here, is the familiar function 1 divided by x. So obviously that 1 over t function inside is the derivative. So the area under that purple curve, if we accumulate area starting from 1, of course, so we wouldn't start at 0 because we're approaching infinity there. So we can't have an infinite integral. But starting from 1, that will give us this area that is slowly growing. So you note that blue curve is slowly increasing because that purple curve is decreasing in area, so it's going to be adding very, very slowly. So with that then, what we end up with is this nice definition of the natural log function. So this is going to be key for us, is that the natural log is defined as this integral. So what that means then also is that if I take the derivative with respect to the natural log of x, which is going to be the derivative with respect to x of this integral, the fundamental theorem of calculus tells us then that the derivative with respect to x of the natural log is simply 1 over x. And that's going to be our key rule that we use throughout the course. That derivative of the natural log is 1 over x. And if you remember us looking at that integral, let's say, from 1 to 2 of 1 over x dx or something like that, when we try to evaluate this with the reverse power rule, what you would end up with is x to the 0, because this is just x to the negative 1. So you would get x to the 0 by anti-differentiating, but that just equals 1. And those areas don't match with the actual graph itself. So now that we have this definition of the natural log and now we have a derivative rule, we can now apply integrals and derivatives because we do know the function is continuous, right? So 1 over t is continuous on the domain from 1 to, on the domain from 1 to x, where x is a positive real number. So clearly we can't reach 0, so we're not going to be approaching 0. We can get close to 0 and do approximations in the other direction, but we'll pretty much not use those. And because they're interchangeable, we'll use what we know about the natural log functions, domain and range. And we know it's concave downward also. So from the graph that we saw earlier, we could see that it's always concave down. So if you took the derivative with respect to x of 1 over x, of course you get negative 1 over x squared, which is concave down everywhere. So we get this nice matching behavior that's going to be extremely useful. Now from my review video, I did discuss some of the properties. Some of them are here in some additional properties are here. So we have the natural log of 1 is 0 because e to the 0 is just 1. The other 4 properties we've discussed. Natural log of e, though, is just using the identity property, so the log base b of b. In this case, we have log base e of e, but for any base value, that's going to equal 1. Similarly, log base b of 1 will always be 0. And then we have this identity that if we have log base b of b to the x, that just equals x by the power property. So that's kind of our inverse operation, right? So the log and the exponential are inverse operations, so they undo each other. And then our inverse relationship is there as well. So now we can look at derivatives. So now we're going to be applying derivatives to our logarithmic functions. And the only thing that we'll note is because the log function is undefined for negative numbers. So I've defined them here pretty clearly, but in most examples, they're going to leave off that information. So we're going to take the derivative assuming that x is positive. So sometimes you'll see it with an absolute value. And this will be more important actually for integration rather than differentiation, but obviously x is going to be a positive number, and then if we're doing the chain rule where u is equal to some function of x, that is also going to yield positive values as well. So for our derivative, again, we're going to get some nice properties here, which is kind of stated in both sides here, which is that the natural log derivative is just 1 over x if it's x. If it is some function of u that is more complicated, then we get our standard f prime of g of x times g prime of x, where again u is equal to g of x. So just the chain rule in its normal form. Okay, so 5.1 covers derivatives. You can go through those examples and kind of work through those and see if you have questions. 5.2, though, is going to be a little bit more because we're going to have to actually take the integral of these functions, so we might need to use u substitutions. So for 5.2, we're going to spend a little bit more time working on examples in the notes. So the log rule for integration, let u be some differentiable function of x. So we're either going to get a very simple version of just 1 over x dx, which is the natural log of, again, the absolute value, which we include unless we are specifically given the domain. So note x cannot be 0 and x cannot be less than 0. So x has to be positive, but if we add the absolute value, that actually extends our domain so that we only have to guarantee that x is not 0. So x being 0 would be the only value we'd have to exclude in that case. And then if we're doing a chain rule application, it's going to require a u sub. So note we're going to apply a u sub. So some change of variables that works out nicely. Okay, so let's go ahead and look at these first examples here. So we'll look at number 1. So we've got t plus 3 over t squared plus 6t plus 7. We can see that the denominator doesn't factor, right? So that might be the first thing that we try here. So since it doesn't factor, we can maybe try to see if we can try a u sub. So we'll let u be our denominator. This will be the typical way we approach derivatives involving the natural log. So then the derivative of u is going to be 2t plus 6 dt. And then we can factor out a 2. And then we get exactly what we're looking for, which is t plus 3 dt. So t plus 3 dt is there, so we just need to divide by 2 on both sides. So 1/2 du is equal to t plus 3 dt, and now we can substitute. This is an indefinite integral. The first 3 here are all indefinite, so we don't need to worry about changing our limits of integration. So what we're going to get is the integral. We can move the 1/2 onto the outside, and we'll have du over u, which is going to give us 1/2 natural log of u plus c. And then we can substitute in are quadratic. And again, we'll leave the absolute values unless we know for sure that we don't have any possible negative numbers. So this function could have negative numbers, the quadratic, so we will leave it with absolute values. All right, so we can do the same thing for the second example here. So we've got 1 over x times the natural log of x squared dx. So now we've got some choices, right? So we could let u equals x squared, or we could let u equal the natural log of x squared, or we could let u equal the natural log of x squared all times x, right? The whole thing in the denominator. So if we're looking at this, clearly it's not going to be the first or the last option here, because the derivative here is going to be really messy, and we would only be looking for dx, which we're definitely not going to get. For the first example, so we could do du, we get 2x dx, so half du is equal to x dx. However, then that just changes our integral to 1/2 of, well, what would it be, right? Because we have x dx here, but this has dx divided by x, not multiplied by x. So neither one of those are going to work. So clearly those are not the ones we want, and so this will be typical if you've got kind of a natural log composite function, you'll let u equal that natural log composite function. All right, so now we're going to apply some derivative rules here. So we'll just note that the derivative with respect to x of ln of x squared is going to apply the chain rule, right? So we've got x squared inside, natural log on the outside. So the derivative of the natural log, of course, is just 1 over our function. So it's just going to be 1 over x squared times the derivative of x squared, which is 2x, and then dx on the end. So that means that du is going to be equal to 2 over x dx, which we can then divide the 2 over to the other side, and now we've got dx over x, which is exactly what we were looking for, right? So we've got dx divided by x, so we can substitute dx over x in our u substitution. So we'll have 1/2 integral, so dx over x just becomes du, so I'll just leave that in the numerator, and then u is just the natural log of x squared, so we'll get 1/2 natural log of, now u is the natural log of x squared, so we're going to get the natural log of x squared, and again we're going to have to put absolute values here, plus c. So we get 1/2 of the natural log of x squared plus c. So it's kind of like a nested logarithm function. All right, so moving on to 3 and 4, again, you can pause the video if you want to try these ones on your own. 3 is an interesting one. There's a couple of different ways you could approach it. But the way I'm going to approach it is going to be a little bit different. So we could do u is equal to x plus 1 and kind of go from there and then rearrange stuff. But I'm going to do something slightly different. Part of the reason is I can notice here that x minus 1 is almost x plus 1, right? So these values are really close to each other. So because of that, I'm going to apply a little trick here. So I'm going to rewrite this as the integral of x plus 1 minus 1 minus 1 over x plus 1 dx. Okay, so let's see if that actually is a legit thing that I just did. Well, all I did was add over a plus 1 and a minus 1. So I just added 1 and subtracted 1, so the net is going to be 0. So this totally works. So that means that our integral could be written as x plus 1 minus 2 over x plus 1 dx. And now I'm going to split the integrals. So I'm going to have x plus 1 over x plus 1 dx minus the integral of 2 over x plus 1 dx. So then my integral on the left simply becomes 1. And then I can bring the 2 out of my integral here, and I'm going to have a simple natural log. So then the integral of 1 is x minus 2. The integral of x plus 1, dx over x plus 1 is going to be the natural log of the absolute value of x plus 1. Note, I don't need to worry about the chain rule here because the derivative of x plus 1 is just 1, and plus c. So this convenient adding and subtracting when you have almost the same expressions is a really useful approach for certain examples. So keep a lookout for those. And then finally, number 4, we're going to get to number 5 as well, but number 4 is our first definite integral. So now we have a set domain that we're going to be evaluating on. E to e squared are perfectly fine values for natural log, so we don't have to worry about undefined values. So for this one, this is very similar to the second example. So we'll let u be the natural log of x. So du is going to be dx over x. So then our integral is going to become the integral of just du over u, right? So we can substitute dx over x as du divided by our u, but our limits of integration do change here. So we'll note that our limits here are in terms of x. So if x is equal to e, then u is equal to the natural log of e, which is just 1. And then if x is equal to e squared, u is equal to the natural log of e squared, which is just 2. So then our integral becomes the integral from 1 to 2. And note now these are in terms of u, obviously, because we've changed variables. So then our answer is simply going to be the natural log of the absolute value of u. We don't need the plus c anymore, evaluated from 1 to 2. Again, we don't have to go back to x because we've changed our limits. So we'll have the natural log of the absolute value of 2 minus the natural log of 1. But note, the natural log of 1 is just 0. So we'll just get the natural log of 2. And if it's a number, you can just take the absolute value as well, or leave it in. So either way is perfectly fine. All right. So finally, we'll look at number 5. Number 5 will be an interesting one. So u is going to, again, be our denominator here, because we can see that the derivative of tangent will be secant squared. So du is going to equal secant squared t dt, which again is exactly what we're looking for to substitute. So we can just directly substitute this. Okay, so our integral is then going to become du over u, the same as our previous example, but we again have to consider, x being 0, x being pi over 4, and how the change of variables will change our limits of integration. So if x is 0, tangent of 0 is just 0, so we get 1, or 0 plus 1. And then tangent of pi over 4 is 1, so we just get 2, which means that we get the exact same integral as number 4. So this is the natural log of u, evaluated from 1 to 2, which will still just give us natural log of 2. Which means if you graph both of those functions, so 1 over x ln of x and this trig function, completely different functions, but they have the exact same area bounded. All right, so that's going to end our first part of the video here on 5.2 with integration. So if you have questions, send me an email or drop by the office hours. So until next time, take care.